Okay, hello everyone. I am the proxy presenter of this paper. So if you have any question, you may drop an email after my presentation to the authors. So in the first part of this report, I'm going to begin with the background of this work. Traditional recommendation systems consider only one type of the user behavior, such as purchase behavior on e-commerce platforms, and present numerous challenges such as the data sparsity, the cold start problem, and others. And these issues result in poor user experience and lower recommendation accuracy. But fortunately, platforms can collect other types of easily occurring behaviors such as click and cart. And these behaviors also contain rich user preferences. Multi-behavior recommendation methods consider these behaviors to mitigate the challenges in single behavior recommendation systems. And in multi-behavior recommendation systems, behaviors are typically categorized into target behavior and auxiliary behavior. And the target behavior is the most concerned behavior by the platform because it directly impacts the platform's revenue, while other behaviors are referred to as auxiliary behaviors. And the purpose of multi-behavior modeling is to use information from auxiliary behaviors to enhance the recommendation performance of the target behavior. Existing multi-behavior recommendation methods can be broadly classified into three categories: the data augmentation, representation aggregation, and representation refinement. The data augmentation methods directly sample from auxiliary behaviors to expand the training data for the target behavior. And representation aggregation methods first separately model each behavior for representation learning and then aggregate the learned representation. And the third method, representation refinement methods, continuously refine user preferences by leveraging dependencies and influences between different behaviors. The variability of user interest is commonly observed across different behaviors. For example, for this user, Lily clicks on the tissue because she's interested in a 100% cotton feature, and she purchases a different type of tissue because it offers a 10% discount, which allows her to save money. And existing methods typically infer user preferences from various auxiliary behaviors and apply them to the target behavior for recommendations. However, this direct transfer can introduce noise to the target behavior due to variations in user attention across different behaviors. So how to effectively avoid the introduction of the noise is a challenge. And they observe that in specific behavior context, users interact with an item only in relation to the features they are most interested in. For example, a 10% discount is sufficient to motivate Lily to purchase the tissue. And Alan clicked on Dune because it is a science fiction movie, and it inspired the authors to model this key feature. And the features, aware from user item interactions within specific behavior contexts, called behavior-specific item-aware preference, are sufficient to predict current behaviors. So if we can accurately capture the item-aware preference in the target behavior, then we can provide effective recommendation. So to address this challenge, there are attempts to design a network that extracts item-aware preferences from each user item interaction, and specifically considering that item-aware preference also exists in auxiliary behavior interactions, they incorporate the data from auxiliary behaviors to assist in training the parameters of the network without introducing information from the auxiliary behaviors. And in the end, they solely utilize the user-aware preferences learned from the target behavior for making recommendations. And there are two advantages to this design. First of all, it avoids the introduction of noise from auxiliary behaviors. And second, it can accurately uncover users' key interests and therefore can enhance the recommendation performance. And this is the design module called Behavior-Contextualized Item Preferences. The module consists of 3 parts: the pre-filtering layer, the item-aware layer, and the post-filtering layer. And the module takes user, item, and behavior embeddings as input and output item-aware preferences mined from specific user-item pair. The pre-filtering layer is used to filter the input user embeddings, and they explicitly encode the behaviors to filter the user embeddings, retaining only the information relevant to the current behavior before learning item-aware preferences within specific behaviors. And the goal of the item-aware layer is to capture the specific preferences of users when interacting with specific items in a behavior-contextualized setting. And for the post-filtering layer, it is similar to the pre-filtering layer, and this layer is designed to better capture the item-aware behavior-specific preferences and further refine them. So they employ the cross-entropy loss function to optimize the network parameters. And finally, they aggregate the item-aware preferences learned from each user-item interaction of the target behavior to provide the final recommendations. And they recognize that to ensure the effectiveness of the BIPN, the input embeddings must contain rich information. And therefore, prior to this, they need to pre-train the embeddings of users and items. And additionally, when interaction data is insufficient, the item-aware preferences learned by the BIPN cannot support the accurate recommendations, and therefore they design 2 additional modules to address these 2 issues. So both of them are implemented by the Light GCN. The embedding pre-training module learns on a graph of all behavior interaction records to maximize information captured in pre-trained embeddings. And the GCN enhancement module learns on the target behavior graph to explore higher-order neighbor information. They combine the representations learned from the BIPN and the GCN enhancement module to perform recommendation for the target behavior. They optimize the model using the BPR loss function, and here the lambda is fixed as the reciprocal of the user interaction numbers in the target behavior. And finally, the model is jointly optimized using the multitask learning, where beta is the hyperparameter and theta represents all of the parameters in their model. As shown in this table, they evaluate the model on 4 real data sets. And it is worth noting that based on average number of interactions, the data can be divided into 2 categories. And in this work, they focus on the top-end recommendation task. And they compare their proposed method with these baselines, including the 2 single behavior methods and 7 multi-behavior methods. The results of the model and all the baselines over the 4 data sets are reported in this table, and it can be found that their proposed method outperform all the baselines consistently across all the test data sets in terms of different metrics. And moreover, they gain some interesting observations. On the data sets with low average interaction of the target behavior, we can observe that the multi-behavior methods are generally superior to the single behavior methods, which can be attributed to the effective alleviation of the data sparsity issues by considering the multi-behavior data. And in the Yelp and MovieLens data sets, there is a sufficient amount of the interaction data in the target behavior to learn user preferences, and therefore, the single behavior method achieved satisfactory performance. However, the modeling of auxiliary behaviors in multi-behavior methods may introduce a significant amount of user preferences unrelated to the target behavior, and therefore compromising the performance. They also conduct the ablation study on 3 components of the proposed method: the embedding pre-training, BIPN, and GCN enhancement. And the table presents the performance after removing each component respectively. And overall, removing any single module from the model results in a performance decline. And these results demonstrate the effectiveness of each component. And in order to further explore the rationality of setting the hyperparameter lambda, they analyzed the different values of lambda, and the results validate the effectiveness of the parameter setting. However, there is still room for the improvements. So to summarize this work, they introduced the behavior-contextualized item preference network, an innovative network designed to distill item-aware preferences from user-item interactions. And the approach employs a 2-pronged design, combine the BIPN and the GCN enhancement, leads to a significant improvement in recommendation performance. And lastly, extensive experiments conducted on 4 real-world datasets have demonstrated the remarkable effectiveness of the proposed model. And thanks for listening. The code is uploaded to the GitHub. If you have any interest, you can download it. And if there's any question, you can drop an email to the authors to this email. Thank you.
Okay, thank you for the presentation.